Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, everyone. It's my pleasure to introduce Yun Mao from University of Pennsylvania. He works on network stuff, including sensor. Okay. Many different areas in networks, such as sensor networks, internet, cable network, consumer networks. So he has a pretty broad research interest. And he also spent a year in UT Austin, work with LeadEQ there. So today he is going to talk about overlay networks. I'll let you start.
All right.
Okay.
All right, thanks. It's my pleasure to be here and visit everybody. So today I'm going to talk about my dissertation work. It's called MOSAIC, a unified platform for dynamic overlay selection and composition. So the internet is a huge success, right? We all believe that. However, it still faces many challenges. For example, there are many new application requirements ranging from mobility, quality of service, content distribution, etc. And many of these new application requirements need in-network processing. And we also live in an untrusted world where there's all kinds of unwanted traffic, such as denial of service attack or spams, etc. And many of these proposed solutions requires in-network defense. Unfortunately, it is very hard to address all these challenges in the current internet architecture. First, it's very hard to change the core of the internet architecture. There are so many core routers in the middle. You can't just snap your fingers and upgrade all the routers all at once. And secondly, protocols are very hard, deeply coupled to their implementations. Take IPv6, for example. Even if you just change the size of your IP address, it's still going to take a lot of effort to just upgrade from IPv4 to IPv6. So many of the researchers got better idea. It's called overlay networks. An overlay network is a virtual network that you can build on top of another network, which can be either a virtual network or a physical network. The internet is a good example to build overlay network on top of it. So with overlay networks, you can achieve new functionality without changing the core of the internet. So that is incrementally deployable. So here's a very classic overlay example. Here's the RON, resilient overlay network, where you have 4 overlay nodes, A, B, C, D here, and the dashed line here represent a virtual link. So that's the link in the overlay network. So whenever something bad happens, say, between node A and B, well, you can reroute your traffic via node C, which, because of the redundancy inside the internet, you can provide a better reliability guarantee in the overlay comparing to the internet. There's other overlay network examples, like in this one, I3 internet indirection infrastructure that can provide you mobility. Say mobility is the problem where the receiver moves around in different networks with a different IP address. So that when the connection is set up, when you move around, the connection is broken. That's what's the problem. So in I3, first of all, the receiver here with the IP1 first registers IP address in the overlay network with certain ID, and push that to what we call trigger here. And then the sender send the packets via the overlay network to the ID. And then when it's reached the trigger, then the trigger is going to forward the packet to the destination. And when you move around, the receiver to a new IP address is going to update your current IP address at the trigger. And then the trigger is going to keep forwarding the packets to the new location to achieve mobility. So this is pretty great, right? And in fact, if you look at the literature of overlay networks in the recent years, there are so many different overlays, Like for resiliency, we have ROM, SOSR, detour, etc., and we have multiple solutions for mobility. And for security, content distribution or scalable lookups, and multicast, etc. So many overlays. However, the problem here is that each of these individual overlays are limited to some specific application domains, and they don't interoperate with each other very well. So what if you want to use achieve multiple properties or application requirements? Like in this example, this is a very simple example where you have Alice and Bob, and they're friends. They want to talk to each other via some video conference or want to transfer some personal files between each other. So first one, Alice, she has a laptop. She moves around and from school to home, and you have different IP address. That's the first challenge, is mobility. And then when Alice is at home, she's behind a NAT box so that her laptop doesn't have a public reachable IP address. So that's the second challenge as of NAT traversal, so that Bob cannot initiate a TCP connection directly to Alice. And then secondly, when Alice's home ISP may experience some BGP configuration problem, where the connectivity is kind of intermittent, so it's not very reliable. Well, the point here is that when you look at all these three challenges, they are, right, yeah.
So I'm going to challenge your first two challenges, which are that I think applications today have largely solved those, right? If you look at Messenger, for instance, right? If I migrate from one IP to the other, that's fine. Messenger client will log on and let me continue chatting with people, doing video chats, voice chats, whatever I want. So why is it that challenge 1 and 2 are compelling?
Well, they're just examples that it impose to certain applications, right? And you can imagine you can build an application that addresses all these challenges, right? But what if you got a new challenge that after you build your application you want to address? In that case, you may probably want to consider something more extensible to solve these issues. Okay, but so I'm going to continue here as my point is that each of individual challenges have been looked at, and there's so many overlay networks that can solve any one of them, but none of them solve all these problems at once. So you can certainly build a new application that solves all the problems at once, but you need to do that for all the applications. And when you have the fourth challenge, you're going to need to deal with that again. And besides, the second issue is that when there's something changes in the environment, such as trust level or connectivity, etc., they may actually invalidate the overlay solution you just chose. So let's see this example here. We have a DHT here as a distributed hash table, but with some network failures. Say a DHT is, I guess everybody in this room knows what a DHT is. So as it's looking up for a key K up there, and then it's routed via certain intermediate overlay nodes and reach the destination R, which is responsible for key K. And then R is going to send back the request to R. However, what if there's some network failures happens between S and R? Well, in this case, well, S is not going to get any results, so that's a lookup failure. And actually, there are many subtle issues in the DHT design that specifically is related to the network failures, so that the connectivity is not transitional. And it's studied by Friedman et al. In the World paper. So
this is the reason not to like overlays.
Well, we got a solution for that, which is use more overlays, right? We already know how to deal with network reliability problems. Just as the first example we look at wrong, we can find another intermediate node T that help you to forward packet from R to T, then to S, therefore to achieve reliability. So what if we can layer the DHT over wrong? That can solve your reliability challenges. Yes.
Classic computer science approach, right? If you can't solve something, just make put on a layer of indirection on top of it, right? So, but obviously you lose things in it, right? You lose the layering sometimes hides information that is useful that comes from lower layers, right? Classic problem with wireless and IP and TCP loss and whatnot. Not only that, I mean, how far up in the hierarchy do you continue this kind of layering? Layering also results in inefficient network stack, right? Because every message now has to have an extra header, it has to be encapsulated, decapsulated, whatever. So, I mean, what prevents somebody from going and saying, okay, this is a great solution. Now let's layer another DHT on top of this DHT to solve some other problem. So continue what? Ad infinitum forever?
Well, but if you think about it, so you can build another DHT that address the reliability problem inside the DHT itself. But conceptually, it is the same as layering different networks together, except that the implementation is different, where you use some kinds of optimizations to solve the layering overhead, such as the network headers. And so this is a good approach for people to test new ideas, to combine different solutions together and to address different challenges for different kinds of network environments. So, well, what we believe that this is our vision of the future of the internet. That is, well, multiple networks will coexist in the future of the internet, right? Because simply one size doesn't fit all. You can't just assume we're going to have an IPVN somewhere that solves all your problems, reliability, mobility, etc., and it works for all your environment, like wireless or wired or etc. This is not going to happen because there's too many network application requirements, and some of them are potentially conflict with each other. And we also have a very diverse environment. So instead, what we believe that in the future of the internet, maybe in the physical level, there's going to be only single network or maybe two. But on the virtual level, there's going to be multiple networks, and each of them is going to be specialized in different application environment. So what's missing here in the internet architecture is that we want to manage all these available networks, virtual overlay networks in particular, and provide interoperability between these networks, and then select and compose existing networks together to provide new functionalities. So to that end, I propose MOSAIC, which is a unified platform with three goals. First, I want to provide a rapid creation and the deployment of new overlay networks, so that when you want to write a new overlays, it's going to be very easy. And secondly, we want to provide dynamic adaptivity for people to select and compose these different networks to suit different purpose. And that may include bridging different networks together and layering them in the case that's suitable. And finally, we want to let the legacy applications today to be able to use these kind of composed networks and to provide low overhead as possible. So in MOSAIC, the network instead looks like this, where you have multiple networks. A packet may traverse 3 different networks just to reach the destination. And at a certain point, if, say, the application requirements ask for this, you may want to layer one of the network on top of the other one just to be able to achieve certain functionality. When the environment changes, you may want to remove that or change it to something else. So there are a few challenges to this approach. The first one is to provide interoperability. It's very hard. If you look at these different overlay networks, they're provided or designed by different people. Network format is, packet formats is different, protocols are different, even the address schemes are different. How can they interoperate with each other? And secondly, protocols are quite deeply coupled with their implementations. If you look at RON, again, for an example here, and go to MIT's website, you download the implementation and say, okay, so this works well for IPv4, and I want to make it work for IPv6. And then you're going to realize, well, there's so many detailed implementations that based on this assumption that we're running on top of IPv4, and so that you have to change so many places, and it's not straightforward. So the other problem is that when you have different network compositions and with multiple networks, you want to check the correctness of this composition. Yes?
I'm sorry, what do you mean by protocols are deeply coupled to implementations?
Meaning, so when they implement the protocol, they based on the assumption that this underlying is IPv4. And so this assumption is built into the implementation of the C code everywhere. For example, like the packet format is IP header, IP format, and you're going to assume an IP header and a fixed length.
I'm confused. Are we talking about Ron? Specifically, Ron assumes IPv4 header? And is that embedded in the protocol description, or is it embedded?
Well, it's not in the description, but it's in the implementation.
So what's the problem?
The problem is you want to maintain the same description, right, for Ron, but you don't want to change your implementation when you change the underlying network.
So Ron assumes IPv4.
But not in the specification.
Yeah, it's just
There is an implementation that
you
is
can write
reduced to
implementations that are agnostic to to whether you're running IPv4 or v6, right? Is that something that's
That's true. That's true. But you have to think to make that in your mind before you design this. And what about if you say you want to run over some other overlay networks that haven't been discovered or designed yet? How do you do that?
Let me ask a more concrete question. What is it about Ron that absolutely requires the underlying layer to be IPv4? Is there anything there? Or
No, there's nothing
Okay.
in the description to ask for the underlying network to be
Right.
IPv4. However, that's written everywhere in the implementation, right? So you want to decouple that. You want somebody to say, okay, this is wrong, the idea of wrong, but you want to write the description rather than in the implementation, so that you can freely change the underlying implementation.
Because what we're starting with is Ron, it's just a research prototype with almost no users. What is this an industry problem that you see beyond?
Well, it is both actually. So if you want to make code running, right, you certainly need a implementation, right? But if you think about the future where you want to run over any overlay network that provide certain abstractions, what's the right way to do that? And it's not as trivial as people think.
So is there another example other than Ron for this particular problem?
Say, let's say you want to build some other protocol, let's see i3, over another overlays, where it provides, say, security or compression. These things are not undoable, right? But you have to deal with that for application-specific purpose. So you want to build i3 specific for encryption or or compression, etc. So yeah. So so our approach, as we talked about earlier, is a declarative approach. That is, we want to specify the protocols in some high-level specifications rather than the low-level implementations. So people don't have to care about the packet format or protocol address schemes, etc. Instead, as you mentioned earlier, we wanted to have the same description of the protocol, but want to be able to run over any kinds of underlying networks. And then this is built on previous work on declarative overlays. However, in their work, it's mainly exploring the conciseness of the protocol representations. But here, we're trying to explore the benefit of a declarative approach in the composition. Namely, the declarative approach provides an opportunity for you to achieve interoperability between different networks. And secondly, it provides the opportunity for you to check the correctness of your composition. That is, if some overlays doesn't work very well with the other one, you want to be able to detect that and reject that kind of composition. So what if we've done this? What impact can we have? Well, first of all, it's going to be a lot easier to build overlay network than currently. I wouldn't be surprised to see that something like if people go on Facebook and click a few buttons, download a new applications so that you can actually easily start a new overlay network built on top of your social network. And secondly, it promotes a new, more novel applications for application-specific networks built on top of composition. Like in the Alice and Bob example, we can actually use I3 and RON and some kind of bridges to achieve mobility, net traversal, and reliability. And in the DHT example, we can build core DHT over RON, and instantly we get a better lookup performance. And if you have out there at an airport or something with public wireless internet access, you can layer I3 on top of the secure overlay to achieve mobility and prevent wireless packet eavesdrop. So there are certainly more opportunities for us to explore in this type of design and implementation. So this is the outline of my talk. First, I'm going to provide an overview of the MOSAIC system, and then I'm going to show you how do you program new overlays in this declarative approach. First, give you some background on declarative networking, and then show you the MOSAIC language we designed for composable overlays so that you can layer or bridge things together. And finally, I'm going to show you how do you compile this composition language into implementation, the details of implementation, and some evaluation result, and conclude the talk. So at a high level, the composition looks like this, where you have the user have a composition specification. That is, you want to use overlay 1, 2, 3, and you want to combine or layer or bridge them in certain ways. And that's the composition specification graph. And besides, you also need to know that which users are, have access control to which certain overlays and where are they going to be deployed, etc. And then the user or the administrator is going to send this specification to a composition server, and the composition server is going to check first whether this composition makes sense, whether it's good design or not, whether it contains conflict interest or not. And then if it does, it's going to generate overlay IDs for each individual overlays and send get the compiled MOSAIC code into preparation and then send it to the real physical node here. So if you have one overlay needed for this case, then it's going to push the code into some physical overlay nodes to build one overlay. If you need two overlays, it's going to build two, and they may certainly be composed together with each other. And finally, after these overlays are built, you can put this meta information back to the composition server so that later people can create new overlays based on the existing overlays as well. So, yeah.
I have a question on the previous slide. I feel a little bit lost about the role of the composition server and what I should think of and its trustedness. That looks like a bunch of routers that it gets to run code on. Who's root on the composition server? And are those distinct administrative domains? Are they a single administrative domain? Can you tell us more about that?
Well, so these physical nodes are running like, so it's pretty much similar to Planet Lab, where say if you are a researcher, you are part of the Planet Lab, you can submit code and run overlays over there. So whenever the user here is the researcher, basically, where you write a specification and you put your tokens or whatever authentication method saying, oh, this is what I want to run. And the composition server is going to use your authentication to push code down there. Whether it's accepted or not, it depends on the privilege set in the physical node.
So should we look at this as an experimentation platform, or is this also the model for, if my work is a wild success and this is how people download overlays over Facebook, it will also be useful in that case?
Yeah, I believe so. So the first step is definitely for experimentation. Then you can, click a few buttons, you deploy an overlay on Planet. That's great. But later, we believe that it's also a good approach for you to design something for social networks like Facebook.
So the model there is that one user gets to run code on all of their social networks. Computers?
If you use Facebook, you have all kinds of privacy or controls, right? And you can definitely set who can or who cannot use my network resource at certain time frame, maybe even. So it can be a lot of different options up there. Yeah. So here's the composition graph that for the Alice and Bob example, where without using composition, you have 3 networks. You have Alice private network, AliceNet, and the internet, and the BobNet. So with composition, it's going to look like this. Well, first of all, we want to layer RON on top of IP to provide reliability. And then we want to bridge these 2 networks, these 2 private networks, AliceNet and RON, together using the Alice's gateway, and then bridge the Bob network with RON using the Bob gateway. And finally, we layer I3 on top of this entire bridge network to provide global mobility access. So, as I mentioned earlier, there are 2 ways to do composition. One is layering, and the other one is bridging. And layering is implemented like this. So protocols are specified using logical addresses rather than IP address. So if you look at the example over here, then overlay 1 is layered on top of IP, so that the underlying address is bind to the IP address. However, if you want to change it, all you need to do is change the binding between your underlying network versus the real network you want to use. So if you change the binding at runtime, it's going to be a dynamic composition that's transit from that graph to this graph. So of course, we can't just randomly change the binding at runtime. So there are certain restrictions we applied here. Is that the restriction on dynamic composition is that for the underlay, what we call for underlying network, the underlays should maintain the same physical node mappings in this case. For bridgings, there are 2 ways to achieve that. First of all, if you have 2 networks and the senders and receivers are on the different networks, they need to share some common nodes as common physical nodes as the gateway. So if you only have 1 gateway, you can set up a static route at the senders, use source routing so that the senders can first send the traffic to the gateway, then to the receiver. Or if you have multiple gateways, in this example, you can use an any-cost service for the sender to select one of the closest node or the node with the least load, etc., to first forward the packet to one of the gateways and then forward it to the receiver. Okay, so
I have a question. So look at this picture. It reminds me of a BGP. I mean, you connect to multiple ISPs, and we all know BGP has many problems. And when you redesigning your new overlay composition protocols, have you thought about how can you solve the existing BGP problem in your framework?
Well, I think this is a lot simpler than the BGP problem because in BGP, you need to deal with multiple service providers. You have different relationship between the ISPs, where here, the nodes are mainly for bridging two networks. So I'm not sure this is.
Do you expect the two networks are owned by the same partner, like same service provider or same operator?
Oh, I see. That's an interesting question. So here we assume that the user have access to this both of the overlay networks. So whether they are the same or not, from the user's perspective, it's the same because the user has the access.
Okay, that usually will be very hard to achieve in practice, right?
Well, I don't really agree with that, but we can talk about offline.
So
yeah.
Why do you have the gateway between two overlay networks?
Well, because they talk in different protocols, and say that one is for reliability, this one is for something else.
I imagine your multiple overlay network basically is multiple instances of the overlay running on the same physical set of nodes. Every node is.
But not necessarily the same setup, right? So in this example, there are two different set of physical nodes.
So if you have a gateway, now that becomes a single point of failure. How do you, even you run wrong on the other side, how do you prevent any failure of the gateway to get in?
Well, you can still use the multiple gateway approach.
Right, if the physical restriction is there's only one node shared between two overlays, no matter what kind of failure resilience scheme you use on the other overlay, it's not going to help you.
That's true in certain sense. However, imagine in a network where the network failures only happens on the left-hand side, right? And the other side, say it's an enterprise network with great zero failure probability, and all the failures happens on the other side. It still makes sense. You want to use this kind of scheme. Okay, so here's the idea of this declarative approach. The core idea is to separate the logical specification from the physical implementation. That is, if you look at these two different approach, in the imperative approach, you have a goal and then you decide how to implement that in C or Java, whatever. Then you push it to the network to run this protocol. But here, when you have a declarative approach, you have a goal, you only declare the high-level goals instead of a low-level implementation. Instead, the system, the MOSAIC system, is going to help you to decide how to implement this and then push it to the network. So there's actually a very similar argument in the database community in the early 70s. That is, how do we want to run database queries? We have a bunch of tables. Do we want to run C-like code to manually say what's the index we want to create and how do we look it up and how do we fetch the tuples, etc. Or we want to write some certain declarative language like SQL so that you can express what you want rather than how or exactly how you want to get the data out of the database. And eventually, we all know that currently people use SQL mostly for the database queries. Yes?
Well, what's the equivalent of the query planner in your system, the thing that does a better job optimizing the code than individual programmers can?
That's a very interesting question. You're probably going to see that later in the talk.
Okay.
Thanks for asking, by the way. The core idea is that, you want to model the entire network state as some kind of a structured data. So in a distributed database. So instead, the entire internet is a huge distributed database where the network protocols is actually the data flow or the implementation of your query language so that you can fetch data or network state from certain nodes. So the benefit is that first, it's very concise programming paradigm. If you compare to C-style implementations, it's going to be like 10 times shorter. And it also provides opportunity to run static check and run safety checks. So here's a quick example of how what this language looks like. If you are familiar with Prolog, the syntax is very similar. And this is based on the data log, which is also a database query language here. So we have each of the lines a rule, and where it's a rule head on the left-hand side and rule body on the right-hand side. Okay. So the input of this program is a link, where you have a source and your destination. There's a link between these two. And the output we want to compute is the reachability of all in the network. So eventually we want to see who's reachable from who in the network. So that's achieved by using these two rules. Here we have a location specifier for this, as it decides where the tuple is stored. So for the link example, it's stored at the source node if I have a link from the source to the destination. So the predicate here means link AB, where there's a link from A to B. And if the reachable means node A can reach node B. Okay, so let's go through the.
So why do you use reachability?
Because that's
in overlay, every node should be connected. Otherwise, you are partitioned.
not necessarily, but the goal to use reachability is to show you that's the easiest network protocols you can write, right, to run the test. So this actually works for all kinds of network, not necessarily overlays.
Right. I mean, do you have an example other than reachability? Reachability is like in overlay. Basically, every parent node should be reachable. Otherwise, there's no meaning to have the.
Well, they're reachable in the physical sense, but not necessarily all reachable. Like somebody if behind the net, I mean, they're reachable, but you can't really set up a connection from node A to node B.
I mean, logical things, every node should be reachable, so you don't need to specify any rule to represent that.
Right. Well, we have. I have other examples. Like we did implement RON or I3 in this type of language, and I have a path vector, type of example. I can show you later offline. So here, the first rule says for all node S and D, well, if there's a link from S to D, then S can reach D. And later, this rule says if there's a link from S to D and Z can reach D, then S can reach D as well. So this is a recursive definition of reachability. By writing these two rules, you can actually let the query processor to design the network flows so that eventually you can compute the O-pair reachability in the network. So as you can see, there's only high-level descriptions of the network protocol. There's no packet format or address schemes, etc. So this one should be as the high-level description as we talk about. So for most
in networks, the way they're configured today, they're not configured for everybody to reach everybody. There's access control lists, there's BGP policy, there's IGP policy. So this transitive closure is expensive, exponentially. You try to apply on an existing.
Right. Well, we're not saying we should run this over the internet, right? This is an example to show you how it actually works as the smallest example to demonstrate the language. So the MOSAIC language for composable overlays provides certain new features. First of all, we want to provide data tuple accessibility from multiple networks so that one data tuple is not specifically binded to a particular network. It should be accessible from multiple of them. And secondly, overlay, we want to integrate the overlay forwarding and control plane so that we can easily create the composition opportunity. There's also other language new features we provide, such as the view support for a functional composition. If you think about the DHT lookup, it's basically a database query with given key K. You want to look up some overlay node N maybe, and that's well modeled in the view, database view abstraction, and we also created certain views for network measurement, etc. Finally, we support some special predicates for TCP and the legacy application uses. Unfortunately, I don't have time to talk about the language features here, so catch me later after the talk if you are interested in this. So here's the addressing scheme in the MOSAIC language. What we are trying to do is to decouple the location from the data. So if you look at this rule here, on the right-hand side, we have CPU load and is bind to L, and the node name is N. So this rule basically says if the CPU load is larger than 20, and we send an alarm tuple to node R, which is defined by an IP address and the port number. And we're going to send our node name of L, node name N and the CPU load, so that alarm server can be notified. The local location is implicit, so that the CPU load can be queried from different networks. It's not specifically binded to the IP network. And secondly, we have this runtime type support for location specifiers. So if you compare these two rules, most of them are very similar, except that how R is constructed here. So instead of being an IP address here, you use a I3 to describe the overlay you're actually running, and the key, which is computed as the hash SHA-1 function of your server's name. So it's very easy to switch from the IP network alarm system to over I3 system if it's what the applications really want. And to integrate the forwarding and the control plane, we provide a standardized data plane interface that's also very simple, as defined by the send with the destination address and packet and receive of a packet. So if you look at the rules on top of there, that's the send rule. So first of all, when you want to send a packet to a certain destination, you do a database join with a routing table using the destination, and you get the next hop here as the address you should send to. And if you can also query the local address. If the local is not your destination, then you're going to forward the packet to the next hop with the same destination address and the packet. So here is how the receive works. So it only will be triggered when local address is the destination. So that is a local receive tuple generated for this overlay. As you can see, the routing table here is not defined in these two rules. Instead, it's defined separately using different MOSAIC rules for control plane. They look quite similar to the reachability example you've seen earlier, but a little more complicated to incorporate like link, cost, and state, etc. So how do we compile these composition specifications into implementations? Well, there are two stages for compiling compositions. First is the validation stage, where we want to verify that this happens at the composition server. We want to validate that this is actually doable in the physical world. And that is when you want to bridge two overlay networks together, you want to make sure that they share some common physical node as the gateways. And when you're layering different networks together, you want to make sure, again, that the higher layer of the node is a subset of the lower level of the physical node in your overlay networks. And finally, you want to check the compatibility between these overlays. Some of the overlays use different approach so that they don't work together very well. For example, when you have an overlay use forward error correction, and the other one use compression, if you mess up with the ordering, you can basically achieve nothing by composing these two overlays together. So the composition server is also responsible for checking that. And after this is validated, you want to compile them actually into the implementations. Yeah?
How do you check something like that?
So far, it's knowledge. It's it's a big table where somebody is compatible with somebody. But I'll talk a little more in the future work.
Okay.
How do you keep track of this as your network evolves? Overlay networks, the way they work today is somebody goes and installs your agent, and now this node is part of your network. Right. So are you watching for network changes and then you go recompose, recompile everything, redeploy? How does that work?
Right. So when network change, you mean the protocols, the overlay protocols actually change, or the?
No, there is a new node in the network.
Uh-huh.
Will you go and recompute the whole thing, or how do you deal with updates? So
I think that's for updates. There's nothing wrong with the compatibility argument there. If there's more nodes, it's going to be compatible.
You have a new
Yeah.
node, which
Right.
makes the upplay no longer a subset of the lower layer.
Right. In that case, this is gonna create some. Well, that's a good point. So we haven't dealt with that in the system right now. So there should be some mechanism to check the dynamic node membership and see if the composition is still valid at runtime. So far we check that at the beginning of the composition stage. Okay. So when you want to compile that, first you maintain that overlay addressing mapping table. That is, you have a network address table at each node where you have an overlay ID and then the specific overlay specific address. And then you generate some kind of a glue code in MOSAIC for layering and bridging. So I'm going to show you, bypass this for time issues, and then I'm going to show you how this works in the Alice and Bob example again. So let me remind you the Alice-Bob example where you have three networks and the common gateways are the Alice gateway and the Bob gateway. And the composition graph look like this. Okay, so because the composition is symmetric, if you look at from both either Alice or Bob's perspective, I just tell the Alice side of this story here, where this is on the left-hand side, this is Alice, and right-hand side, this is the Alice gateway. So initially, where we don't have any overlays, but we still have the internet and the private network. So as you can see, some predefined tuples exist in this network net address table, where 0 means the internet, and we have this IP address defined. And the overlay ID is Alice net with a private IP address. On the other side, the Alice node has another private IP address. So the first thing we want to do is we want to layer run over IP, if you can remember the example. So this is very simple to achieve here. That is, the composition server inserts one rule here that says we want to bind the network address table with the internet address of the specific address to the run's underlay table. In that case, it's create this certain layering in this figure. And then it's going to insert another address as with the run overlay ID and the run specific network address. And secondly, we want to bridge these two networks, Alice network and the Bob network, and to provide a unified, so that the Alice is reachable out from outside the network. So that is achieved by creating a source routing address from, first of all, to reach the wrong node here at the Alice gateway, then reach the Alice's private network address. And finally, we want to create another layering that is I3 on top of the bridge of the network, so that we bind the network address of the bridge network to the I3's overlay address. As you can see, the I3 the addressing scheme is totally different from the IP address, but still you can store that very well in the polymorphic network address table. So after creating this binding, you actually already build the entire composed overlays. And here is how the data flows from Bob to Alice. So when Bob wants to send a packet using the I3 network, it's going to use the I3 and with the I3 address as Alice ID, which is a secure hash of Alice's node name. And then the I3 module is going to look it up and find what's the real, what's the underlying network address for I3, which is the source routing address I just showed you earlier for the bridge in the network. And then the botnet is going to forwarding using the first element in this source routing to forward it all the way to the Alice gateway node. Here, then we take out the first element and forward using the second element of the source routing address and let it reach the destination Alice. So here in the middle, we have a few intermediate round nodes. So they don't exist usually if there's no network failure happens. However, they will kick in if there's some failures detected in the middle of the network. And so that creates a certain indirection in the network. So here.
So are these rules specified manually or automatically generated?
These rules are generated by the composition server from, well, you need to specify the graph using the XML language.
So what kind of graph I need to specify? Like, do I need to specify where to connect the two overlays?
Yes, you need to specify the gateway nodes. So that's what I mentioned in the specific composition specification. That is, what's the overlay you want to use, how are they connected, bridging or layering, and what's the common nodes to provide bridging in this case. So, but these.
How this decision was made?
So far, it's made by the human being, like the administrator of your network.
Okay. But I mean, as a user, I only care about end-to-end, right? I don't want to use any expert knowledge to decide where to connect the two overlays to satisfy my end-to-end requirements. I just want to, for example, I want reachability, security, like some end-to-end performance requirements. And how do you have any help to select which node will help you achieve these?
That's a good point. Yeah. So eventually, we want to be able to provide that, right? I mean, it's going to make the user's life a lot easier. Just say we want that property and what's the appropriate network. And maybe for reliability, there are zillions of different algorithms you can use. What's the right one for me to use given the current environment? Yeah, that's one of the future goals we're looking at. Okay, so this example shows you the dynamic composition of chord over run. So on the left-hand side here, chord is directly layered on top of IP, but here we insert run in the middle. This is achieved by joining the two tables here, network address table and the switching underlay table. That is, when the switching underlay table stores the overlay ID 0, meaning the IP network, then this composition scenario is happening. But if you change it to the wrong overlay ID, then it's going to dynamically switch to the right-hand side. So the implementation scheme look like this picture, where we take over the network layer in MOSAIC and provide a send and receive semantics to the upper transport layer. And then when you have built the overlay protocols in the MOSLog, it's going to first be sent to a compiler that's translated into some data flow language. And then it was sent to the runtime system here, which maintains the network flows and calculate network state and store them in the local tables. So there's a multiplexer in the middle that, based on the overlay specific address, it's going to send and forward back and forth for different packets to the right module in this example. So here's a deeper look out of this small graph here for a particular overlay. And this may, if you know how click router works, and this is very similar as the data flow elements kind of an extensible router idea. So when the network package comes in, it's going to first go through certain overlay multiplexers. It's going to see whether this package is overlay 1 or 2, and then make it the right format, and then send it a queue, and then push it into the real implementation here in the middle. This is what we call the root strand here. Each of the root strand is a list of elements, smaller elements as in the click elements here, but with some particular database operators. So each of the root strand here correspond to one of the rules you see in the MOSAIC code. So we did certain optimizations to improve the performance of this data flow graph. So there are two ways to automatically improve the data flow performance. One is called local event shortcut. So imagine we have a data flow like this, where the network inflow is on the left-hand side, outflow is on the right-hand side. So this event, when we compile the rules, we know that this is going to be a local event, where it's not going to be sent out of the network to other physical nodes. Instead, these two are local events. So we create a local event shortcut in the data flow to make it look like this, where you don't have to go through all the scheduling in the overhead in the system. However, the second optimization technique is called inline expansion. This is similar to, like in C language, where you have an inline function. You can instantiate the code in multiple places. Like in this example, I want to duplicate these two database operators, so that we don't have to worry about the concurrency issues, like in this example created from the MUX. So now the throughput is increased. So if you have a multi-core or processor, you can take advantage of multiple threads in this example. So another optimization is from the compilers. It's called a tail recursion view optimization. So imagine a naive DHT lookup based on a ring, where the pseudocode looks like this. If you have a node key k between you and your successor, then you return the address directly. Otherwise, you run a recursive lookup. So if you directly compile that, in our language, the communication pattern look like this. It's going to first send up a bunch of requests as the recursive functions, and then send it back to S. So our compiler is going to find out the pattern that this is actually a recursive function calls. So in this case, you can convert the recursions into iterations, and therefore what's actually end up happening is the end node R here is going to directly send back the packet back to S to avoid the middle overhead as the latency involved. Okay, so in terms of implementation, we built this for mostly Linux implementation. Windows is not supported yet. So we use some tunneling techniques as the pseudo tunneling device, it's TUN device. And for applications, we support ping or wget or Apache, etc., all these standard TCP applications. To measure about the overhead, we compare the simplest rule here just in a cluster environment. So this is a controlled environment, just want to measure the overhead. So we found out that in throughput, the overhead compared to the native point-to-point UDP tunnel implementation, we use OpenVPN in this case, is only 7%. And if you look at the latency, it's only 0.25 milliseconds more extra overhead compared to OpenVPN. And this is not as significant in the wide area environment. And we also try to see how the data flow optimization help in the implementation, and realize that in terms of throughput, the optimization can increase the throughput up to 10 times of the original implementation. Yeah.
Are you saying that it's 10 times better than the OpenVPN implementation?
No.
Okay. Okay.
OpenVPN is the theoretical bound you can do, right?
Okay.
It's not magic. It's the optimization compared to without optimization.
You said this was the simplest rule?
Right. So that's to create the point-to-point tunneling.
Okay.
And if you want to look at the complicated examples, they're right here. So we're going to revisit these two examples, right? Alice and Bob. We have set up the environment like this. This is an Alice node in New Jersey where I live, and we use a bunch of Planet Lab nodes as the overlay nodes for I3 and Run, and Bob somewhere in Utah, which is pretty much the Emu Lab nodes I take advantage of. And so the performance looked like this. We want to set up a file transfer from Alice to Bob and see what's the performance impact. However, it's actually not doable directly in IP because both Alice and Bob are behind in that box. So we had to set up some port forwarding at Alice's gateway to make that happen. And then that's the direct IP line here. So this x-axis is the time we elapsed during the experimentation. And y-axis here is the throughput. So in the middle of here, between 30 seconds and 60 seconds, we inject certain failures by using some IP firewall rules just to block all the traffic sent directly from Bob, so that the throughput of direct IP connection dropped to 0. And then we remove the failures, and then it go back to whatever it is here and finish the file download. In the second case, in the MOSAIC case, where the node is composed on I3 on top of Run, so because Run provides resiliency, it can reroute the traffic out to some intermediate node in one of the Planet Lab nodes, so that the throughput is maintained. As a result, the download finished earlier in the MOSAIC case. Yeah.
Is that in kilobits per second?
I'm sorry?
What throughput y-axis, is that in kilobits per second?
Yeah.
And what are the causes of those intermediate drops in the MOSAIC case?
Well, we believe that's the scheduling overhead in the Planet Lab node is not very predictable in our case. So it creates certain interaction that for certain times, as you can see, it drops a little bit. So in here, it's actually predictable because even for Run, you need some time to detect the failures and reroute the traffic, right? So it actually drops a little bit when the failure first happens, but it will come back immediately after the failure is detected. Okay, so for the next experiment we run, we compare a CORD over IP versus CORD over Run. So again, we inject certain failures in the middle of the lookups. And the y-axis here is lookup accuracy. That is, can you give me the right node that's responsible for the particular key K? So again, as you can see, when we inject failures, the performance of CORD lookup dropped to very low, but the CORD over Run still maintains very high lookup accuracy.
Can you define how you injected failures?
I'm sorry?
How did you inject failures?
Well, we use firewall rules to block traffic from one node to another. This is how we inject failures. Yeah.
Yeah, that is a strange and surprising failure mode for CORD. Could you explain again what is lookup accuracy and why is it plummeting?
Okay, so lookup accuracy, means when you look up a key K without failure, everything is stable. Which node is what's the right node? And when there's a failure, two things are going to happen. Either is the CORD is going to trying to fix that, and the return path is going to be broken, so you're not going to get any results back So that's one mode of failure. But the other is that it's going to be inconsistent. Some of the nodes is going to get back the right result if the lookup path is not affected by the failures in the network. Some other nodes is going to get some other, different nodes as the lookup result. So I call that inconsistent in this case.
I'm going to suggest that you finish your talk now, and so that, and then the rest of the questions, we can hold back the questions for a little bit. Till you actually end it.
Okay, sure. Yeah, thanks. So pretty much, well, as a bottom line of this talk, I hope you were convinced that there's going to be multiple networks, especially virtual overlay networks, that will coexist in the future of the internet. So my contribution of this talk is that, first of all, we present this MOSAIC platform, which is a unified platform to provide node. You can in the network platform, you can develop and deploy, select, and compose different overlay networks together. And the second contribution is the MOSAIC language to specify composable overlays. And finally, the last contribution is an efficient runtime prototype for you to test different overlay ideas. So in terms of future direction, there are a few steps we can take immediately in the MOSAIC platform. That is, first of all, we want to unify protocols in different layers other than network layers. So far we deal with overlays in network layer, but there are also interesting overlays that you can design in, say, transport layer to provide different application requirements. So how can we incorporate these different network protocols at different layer and maybe provide an opportunity for you to do cross-layering optimizations? And secondly, we want to reason end-to-end the properties of composed overlays based on the overlay specification so that you can automatically reason about which overlay is compatible with the other overlays. And we have an edge here because we are doing this in a high-level description language with a logic-based language. So there's a lot of related work that we can leverage on using this idea. And finally, we want to provide the automatic composition. That is what basically Ming suggested. That is, the user gives some high-level descriptions. We want security, reliability, and the system is going to automatically suggest you the right overlays to select and compose to realize this, to create the composed networks. So going beyond the overlay networks, I think in the next generation of the internet, there's going to be a lot of exciting new problems, especially if you look around your laptops or desktop. That's not going to be the only devices that's hooked up to the internet. There's going to be a lot of different devices, like personal devices like your iPhone or whatever PDA you have, or embedded devices like sensors that monitor different things from your car or your home, your refrigerator, etc. And there's going to be multiple interesting protocols and networks be deployed in the internet. How do we incorporate them together? Well, it's maybe not too hard to provide connectivity for a certain period, but how do you manage all these different protocols and networks? Especially, there are many things like you can want to be able to detect, say, failures in the network, or want to reason about why you got certain unexpected state and you shouldn't get in the first place, and maybe finally to predict what's going to happen in the future based on currently what you have observed. And there's a lot of interesting work from interdisciplinary research that I think is promising, say, by using different database technologies or machine learnings to understand the networks. So I also did a few other works during my PhD period. For example, I did one scalable network protocol in sensor network, which is is called S4. And I also look at using machine learning techniques to in the networking settings to detect failures and reason about missing network topologies and estimate network distance. And finally, I also worked on host mobility problems and provide an overlay-based host mobility as a session layer to provide different application support. That's it.
Has your thesis work also appeared in a publication?
Not yet. It's in submission.
Any other questions?
How much work was it to convert i3 and core to your language?
So i3 over there, that's only 16 rules, given that chord is implemented by somebody else. Well, chord in our language is only 35 lines of rules. So it's there. I admit that there's a learning curve because people, they're trained by doing things in C or Java, not in Prolog. But once you get used to the programming paradigm, you're gonna learn that much quicker, and you can design all these different overlays in a very concise kind of way. Yeah.
How much different is your language comparing with Bohm's original paper?
Right.
His
So-
declarative language.
So the difference are let me see.
Maybe generalize expand the question a little bit into the relation with data log and sort of the other efforts in the declarative effort.
Okay. Okay. So there's data log, which is not a distributed version of current database. So Boone, my advisor, in his thesis, extend that to run distributed recursive computations using the data log syntax and to run queries and implement protocols. But what he's looking at is mainly a single overlay network, the control plane. How do you implement that in the language? So in the MOSAIC, there's the focus is different. We're looking at multiple networks. So like the way to access tuple and the addressing schemes are different. And the language features mainly to provide a functional composition is different. So we have view support, which is it does not exist in the ND log, which is Boone's work. And there's also different predicates to make this practical, so that you can use for like legacy applications like wget or Apache. And this is also not in the ND log example.
People are trying to understand what it means to have a short implementation. If I look at something like OSPF, what is it doing? It just shows paths. I mean, it's 1 page of a textbook, but the specification runs probably about 40 pages, 40, 50 pages. Because it's about all these other things, that are not just shortest path forward. So wouldn't that happen with your protocol if it was a real artifact?
Well, it's certainly not going to go away, but the argument here is that if you do that in a controlled way, and that's automatically implemented by and considered well by the runtime system like MOSAIC, so that you can translate the high-level description into the implementation. And because the system should be able to custom the protocol to different environment, that's what the declarative approach wants to achieve.
So when you said that you implemented I3 by specifying only 11 rules, obviously the original implementation of I3 is probably thousands of lines of C code. Right? So how did all that complexity get rid of? When you say that you implemented I3, do you mean that you implemented something that would interoperate with another existing I3 network, or did you mean you implemented I3-like functionality?
Right.
But how do you know you implemented all of I3's functionality?
Well, look up the paper, and they provide ABCD functionalities, and then we implement that. That's pretty much it. So if you look at I3's implementation, a lot of code is dealing with chord. and especially the embedded chord implementation in the I3
Fine,
implementation.
let's talk about chord. You said that chord was 35 lines of code, right? The original chord implementation is pretty large. So how did you manage to hide all that complexity into 35 lines? What about simple stuff like generating packets, or when you compile the rules and that then becomes C code that's thousands of lines? Is that what you're saying? I'm confused.
I'm sorry, what's...
You compile the code, right? This is the rules that you like, right? Let me put this right. When you write a protocol, a lot of the code is not necessarily the core that implements the state engine. That's usually, that's the most important piece of code, and it's pretty small, tightly, well-defined. But then there's a lot of code that deals with packet formats, headers, making sure that everything runs efficiently. What happens to all of that code in your language?
That's been hidden away, but it's in the MOSAIC runtime system, but it's not in the rules, because that's some code that all the overlay protocols can share, right? So, So what I'm saying is there are commonalities between and you can take advantage of between these overlay protocols. So when they share certain like packet format or addressing schemes, these can be taken care of by the system, MOSAIC system. So if you compare Chord C implementation versus the rules, there's not many similarities. But if you compile the rules into implementation, and then you compile the C-style implementation in the data flow format, and there are a lot of similarities between these two implementations. So the contribution here is the compiler that can translate the high-level stuff into the low-level implementation.
Okay, last question.
So all these overlays can work with the same. I feel like you're saying that it's important to have a messaging layer, right? Something that can kind of take a logical address in some blob and either encapsulate it or do send on it, and that's a good abstraction for many overlays. What is it that is also being added by the compiler, right? There's the state engine, there's a messaging layer. Is there an additional thing, or is that really how I should think about the compiled protocol?
So I think there's the parallelism is probably another one that you can take advantage out of this implementation. So sometimes you can, in the protocol, if it's not specified, you can probably send out probing, say, at the same time, multiple packets and timeouts, etc. And there are specific language constructs that you can deal with that I didn't talk about, like soft state in this example. We support tables with soft state, which is usually if you have an implementation, you need to take care of that by yourself. So here the language construct help you with that. But I didn't talk about this in the talk. We can talk about that later offline.
Okay. So let's thank the speaker.
Thank you.